All right, thanks very much, Rachel. It's a pleasure to be here. I gave a general title because I wasn't sure which thing I wanted to talk about. So I'm going to talk both about binary black hole accretion and off-axis jets coming from merging neutron stars. And I've grouped them together because they're both simulations we do at NYU to understand electromagnetic counterparts to gravitational wave sources. So but let me start with binary black hole accretion. That's something I've been working on recently, so I'm very excited about it. And this is work that's done with Jonathan Zweig at Columbia and Zoltan Hyman at Columbia and two students at NYU. And the idea is both supermassive black hole binaries that are LISA sources and PTA sources, but also potentially stellar mass binaries in gas. That could be if they're in an AGN disk, as is popular here, or potentially some more exotic scenarios. But the basic problem is a beautiful one. It's just replacing a Shakura-Sunyaev disk, replacing the central point mass with a binary, and seeing what happens. Okay, and there's some similarities with some of the physics of protoplanetary disks as well. So the story for the supermassive black hole binaries, it might be good to turn off those lights if it's possible.
It's one of the other slides.
Yeah, thanks. It'll just look nicer. Okay.
Great.
Is that, as we know, galaxies merge and they have a lot of blue light in them, so there's gas in these merging galaxies. There's lots of beautiful images like this. And we also know that each of those merging galaxies likely has a supermassive black hole at its center. So the question is, what happens after those black holes after the galaxies merge? They're embedded in a merger remnant, which probably looks something like this. It's a messy galaxy, and in fact there is a quasar here. And so the question is, if it's two black holes instead of one, what are the observational signatures of that? And also, what does the gas do dynamically to the binary? Okay, so the kinds of things that we want to understand is that if the gas cools and forms an accretion disk around the binary, there's going to be viscous stress in the circumbinary disk, which is going to drive gas slowly towards the center. But afterwards, there's tidal torques from the binary that are going to interact with the gas. And the question is, do those torques cause the binary to merge or possibly separate? And so that's a very interesting topic right now to understand. If the black holes are emitting gravitational radiation, then the gas torques can affect the rate at which those gravitational waves are emitted, and it may affect the signal. That's very important to understand. What was thought for a long time is that the binary carves out a cavity at the center of the disk, just because gas is being rejected by a kind of propeller-like effect. And we do find that, but we'll see that the story is a lot more interesting than just having a hole in the middle. And then there's this also idea that when the gravitational waves take over, that the black holes would decouple from the disk and merge as a dry merger. But we find that's not the case either. So there's lots of interesting things that were kind of unexpected that made this project really fun. That's why I'm really happy to talk about it. And so these are types of questions. We're going to know how hollow is the cavity? Is there an imprint of the binary on the accretion rate? And how is the accreted mass divided between the binary components? Does it drive the mass ratio to 1, or does it make it smaller? And then also, how are the spectra modified? So these are all interesting questions. So the kind of old picture, this is just a cartoon. We're going to look at simulations later, so it's kind of nice to have a simple picture first. And this is not to scale at all, but the idea is that the binary orbits in this cavity, and there's a circumbinary accretion disk. And the idea was that the binary would excite waves in the circumbinary disk, and that non-axisymmetric density structure would torque the binary and potentially cause it to change its angular momentum and energy. And then the idea was, at some point, if the black holes were starting to get closer, at some point that's a gravitational wave. Gravitational waves take over, and then those black holes are emitting on a new relativistic timescale and potentially leaving the disk behind. During the viscous evolution time, as the black holes got closer, the disk kind of follows it. So it's kind of self-similar. There's a phase like that until the gravitational waves take over. Then you have a merger, and then assuming there's no kick, of course there is a kick, we know, but just for simplicity, assuming it sits there, then on a viscous time, the gas would then fill that cavity, accrete onto the single black hole, and emit light. That's the old picture. Okay. So the other thing that we've also worked on is the idea that when the black holes merge, the merger remnant, the black hole, is less massive. So the disk has to adjust to that effect of emitting a few percent of the rest mass of the black holes as gravitational waves. But also the kick of the black hole, the disk has to respond now to the fact that the merged black hole is moving, and that sends a spiral shock through the disk. And all of these things produce potential observable signatures, so counterparts to the gravitational waves at different times. So, okay, so the question is that we started working on a few years ago is this picture correct? And the answer is no, but parts of it are. To do this, we used a really nice code written by Paul Duffel, who was my student a few years ago. He's now at the ITC at Harvard. And the idea is, let me see if this works, is to use a hydrodynamics code where the mesh is able to move and distort with the fluid. This is just a test to show you, it's just kind of a cool thing to see, but the code is Lagrangian in the sense that the mesh distorts with the fluid as it flows, and it can resolve really low, things at very low resolution. So it's a very powerful code. It's particularly good for disks that are supersonic, because you don't want to be passing fluid through a grid that's at rest supersonically many times, because there's numerical error that accumulates. So it's better to have the mesh move with the fluid, and that allows for much more accurate integrations of the equations, in this case of relativistic MHD. Okay, and because I think a lot of you here are familiar with this, just a slightly technical point, is that these codes are all, these Godunov codes for numerical compressible hydrodynamics, are all based on the solution to the Riemann problem, a shock tube, where you get fluxes of mass, momentum, and energy due to the solution of this Riemann problem that's known analytically. And you get these fluxes, and typically you find the flux at the zone interface that's at a fixed space point x. As a function of time, you have the self-similar solution of this Riemann fan that expands away. But the cool thing to notice is that we know the solution at any point in space-time. And so in particular, the face of the numerical code is moving at some velocity. We can calculate the flux with respect to a moving face. And if that face is moving at the fluid local speed, then there's very little flux. So the only fluxes are the really interesting fluxes due to gravity or some other interesting instability, but not due to bulk motion of the fluid. So that's the main technical improvement of this code. I'm going to show you both for these disk simulations, but also obviously for explosions, the same thing is important. Okay, so the version that we use for the disk is called Disco. And the idea is, instead of having Voronoi cells, because we know that most of the motion is azimuthal in the phi direction, we use cells that move locally at the Kepler speed, but they don't change their shape, and that helps to reduce noise. So it's just an improvement to get the accuracy of having a Lagrangian code without introducing too much extra spurious noise, potentially. Okay, so here's the thing that we did 2 years ago. This is my student, Yaiki Tang. And this is what it kind of looks like. This is the center part of it, and we're in the co-rotating frame of the binary. So you can see that there is kind of a cavity, but it's not empty. And what happens is gas gets scoured from the edge of the disk and forms mini disks, what we call mini disks, around each black hole. And then gas is shared back and forth and is accreting onto each individual black hole. So it's not the case that the black holes are dry. They're, in fact, if there's a circumbinary disk, we find in this case where the masses are the same for each component, that gas does make it to the center, and there's all types of interesting shocks that produce X-rays and bright emission. And furthermore, this gas interacts gravitationally with the binary and can affect its orbit. Okay, so the idea in this talk is that there is a cavity, but it's not round, it's eccentric, as you saw. It's off-center, and that's important because it means some of the gas is close to the binary at any given time. This is an instability that always develops even for an equal mass binary. You still get this sloshing, and you get this eccentric cavity. There are gas streams that connect the circumbinary disk with each black hole. Each black hole acquires a mini disk, so its own accretion disk that's being fed by circumbinary accretion onto each disk. And there's some very interesting physics there. What I'm going to show you is that these disks do not require viscosity to accrete. They are torqued and tidally squeezed by their companion, which allows them to accrete due to a shock, a spiral shock, which is really interesting. The other thing that you saw in that movie is that there's a lump of gas that's being ejected by the binary that tends to accumulate, and this introduces a new timescale in the problem. There's a slower rate which this lump dumps back mass onto the binary, and that lower frequency could be the dominant frequency. So if you see a quasar that's varying at some frequency, it's not necessarily the binary frequency, it could be this lump frequency that can dominate, which would mean the binary frequency is higher, which means that it could plausibly be in the gravitational wave emitting regime already. There's a quasar that's kind of famous that hints that could be possible, and there's others as well, that might be the case. All of these things radiate. The streams shock when they hit the disk. The mini disk is hot. It has a spiral shock wave in it, as we'll see. The outer disk also emits. So these are bright sources. They're very bright. They're not dark as was previously expected. Okay, so the next thing, in that first simulation, the black holes were on a fixed orbit and they just stayed there. In this case, we're going to show a binary that's emitting gravitational waves, so it's starting to merge. And what's going to happen is the gas is interacting with it. And again, we're in the co-rotating frame of the binary. You can see gas shared back and forth between the black holes. But if you can notice, it's going to speed up. As the black holes in spiral due to gravitational wave emission, their frequency goes up. So the gas is going to kind of interact. What you should notice is as they get closer together, the gas does not decouple. So even as they're starting to merge, they're dragging gas, and now it's really going fast. And all the way up until merger, and this is the very end, there's still gas streams connecting to the black holes. So it's not the case that the black holes decouple from the gas and just merge in vacuum. They merge with gas, which is really important for potential gravitation, for electromagnetic counterparts potentially. The other interesting thing is there's some interesting structures in the gas, which could be important if the black hole gets a kick and is pushed through these things. Kiara?
How much gas, like how much mass is there in gas with respect to the black hole?
Yeah. So this is these can be scaled. We're in the limit that the mass of the disk is small compared to the mass of the binary. So there's no self-gravity. So we can, depending on how much gas you think is in the center of a given galaxy, we can scale the simulation. So sigma is a scalable parameter.
Okay.
So yeah, in the case that if this mass becomes comparable to the mass of the binary, we solve self-gravity, and we are doing that as well. But I'm not going to show you here. I can show you later if you're interested. Bill?
So, Andrew, so time average, how much mass is going through this in the viscous case versus how much mass is going into the black holes?
We get quasi-steady state, so it's really amazing.
So
all of the gas.
M dot black hole is the same as M dot through the disk.
Yeah, it's all being accreted. This is amazing. So it's not. So I should say this is Mach number dependent. So everything I'm showing you is at Mach 10, which means h over r is 0.1, which is a bit thicker than real disks, but we have to do it for numerical reasons. As we go to higher Mach number disks, thinner disks, the accretion is less efficient. So that's something we're exploring now. So keep that as an important caveat. But for these Mach 10 disks, they accrete efficiently.
So I remember over maybe 13 years ago, you did the same experiment with Milos, right? And there you got basically a reduction, about a tenth of it went to the black hole.
We got less accretion, but the difference with that was the early simulation, is we extracted the binary. So we had an absorbing inner boundary condition here, so we didn't have the interaction of the gas as it formed the mini disks. So that was it was already interesting that it was 10% instead of 0, but now when we include the black holes in this simulation, we get even more accretion. Okay, so here's the interesting thing, is if you look in the top, here's the gravitational wave strain from the binary, and here is the accretion rate and the luminosity in the X-ray. So what we see is this modulation on the binary frequency, but we also see this lower frequency due to that lump that's dumping mass onto the binary at a different frequency. That's an interesting thing. But what you can see is all the way up, and so this is early time, but later, now it's starting to in-spiral and merge, there's still accretion. And so what happens at first is they're pulsing together, but these higher frequency, higher energy X-rays are kind of noisier. But near the end, they both start to pulse together with the black hole gravitational wave source. So this is a way to look at a quasar, both in the soft and hard X-rays. If you see one that's starting to pulse together, that means that it's close to merger. Yeah.
But Andrew, you're not including the effect of the radiation on the gas, right? Like the feedback.
No, and that's a huge simplification. So yeah, that's, I probably should, I'll list them later,
Wash
but
out a lot of this.
yeah, it could. So these, yeah, there's the radiation hydro, which is now being done for the single black hole case, needs absolutely to be done for this. So that's a huge caveat as well, yeah. So, but it will be done soon, and yeah.
So for angular momentum transport for the normal kind of AGN disks,
Mhm.
people suggest alpha thin disks, you know. Do you also use that, even though you're not a full thin disk for angular momentum transport?
Did we use an alpha?
Yeah.
Yeah. Yeah, so
it's not fully thin, as you said, it's kind of thicker than
yeah.
people assume when they talk about a thin disk.
That's right. So 0.1 is kind of marginal, but we do it for numerical reasons. The viscous time becomes very long for a truly thin disk, so it's computationally difficult. But we do use an alpha prescription for the viscosity, which is something that's kind of okay because we're just delivering mass to the binary, and most of the dynamics is kind of gravitational, so it's just applying some mass. But absolutely, there are, our goal is to then do this. It's already very challenging to do this because there are disparate timescales of the mini disk and the circumbinary disk. So it's very hard to do in 3D with MHD, but that is where we're going. Yes?
You said this was MHD, so does the...
No, this is not. This is viscous hydro.
But would you think that the mini disk could support magnetic fields and get outflows or even jets?
Yeah, it absolutely should. So these are, yeah, so that's that. And people have done, for just a few orbits, 3D general relativistic MHD. And they find results that are roughly in agreement with what we're showing here. But the problem is, these systems evolve in a viscous time of the circumbinary disk. So just doing 2D viscous hydro is already really challenging to do for the time scales of interest. So you can do a kind of a zoomed in simulation in 3D with MHD, but you can only do it for a few orbits currently. So the goal is to soon be able to do that for longer time scales. Yeah, so but that could absolutely change the physics near each mini disk. Kiara, yeah.
This is my last question.
No, it's okay.
How would the actual gravitational wave emission affect the electromagnetic signature that you're seeing in this disk?
So the gravitational waves probably don't couple strongly to the gas themselves, but
surely they would be, you would have this stretching and squashing of the space-time
Yeah.
around it, and so if you have this periodic signature that's happening because of the accretion physics, then this might further modulate that signature?
Yes, that's certainly the case, but that's probably a relatively weak effect. People have made that claim, but it's a very small effect. What's probably more important is the gas effect on the black hole orbits that affects the gravitational waves.
Okay.
Yeah. Yes.
So just as a technical question, so you're using DISCO for this?
Yes.
Right? DISCO is cylindrical
Yes.
grid, right?
Yes.
You have two black holes, so how do you resolve that? Do you have cylindrical grids on each one and interpolate, or?
So the black holes are on the grid,
Yeah.
and they're represented as sync particles, as I'll describe a little bit later.
Right.
So they move through the grid,
Yeah.
but the grid is rotating with the black holes
Okay.
locally.
All right. But then locally around each black hole then is essentially a rectangular grid, not a cylindrical.
It's even weirder than that. It's kind of a cylindrical grid that's at the center of mass of the binary. But yeah.
So for those mini disks around that, you're really suffering from the fact that you have grid effects there. That
Somewhat.
Was the argument for using DISCO in the first place, to avoid these grid effects.
The advantage of DISCO is that locally the mesh is co-rotating with the black holes.
Okay.
So you're right though, the shape of the zones is a little bit funny.
Right.
But it works. So there's still gas orbiting each black hole in a mini
But
disk.
it is supersonic relative to the grid though.
But the grid is rotating with the black hole. So otherwise you'd have gas that was orbiting each black hole plus being infected supersonically around.
Right.
So we avoid that problem. But yeah. But I'll show you a little bit later. We try other things as well. Yeah. Okay. Other questions? Okay. Good. So here's an interesting thing. This is the total torque as a function of m dot. And we found that when we represent the black hole, we can't resolve it yet because there's a separation of scales. We're trying to do this whole circumbinary disk. And then the ISCO, the last stable orbit of each black hole, is too small to resolve. It's just impossible for LISA and PTA sources. So what we do is we have a sync prescription where we just remove mass around each black hole, and that's called T-sync, that's tau sync, that's our parameter for moving mass. We found something really interesting, which is the sign of the torque depends on our model for moving mass. And in fact, if we remove it quickly, as would be the appropriate case if we were resolving the ISCO of each black hole, the torque is positive. So that's kind of surprising. So it could be the case that black holes, the effect of gas, if they're emitting gravitational waves, is to slow down their in-spiral. Or if they're far enough away that gravitational wave emission is not yet important, then they could actually cause the black holes to separate instead of merge. So this is something that we're trying to understand really carefully because it's obviously an important question. But we do find that in at least some cases, the torques are positive. And if you look at why, it's a subtle thing. This is a torque map. So here's a positive torque and a negative torque. So it's an imbalance between the gas that's right near each black hole. So there's both a positive torque and a negative torque, and they're almost exactly in balance, but depending on the sync rate, this tau sync, the net torque can either be positive or negative. So this is quite interesting, and this may in fact be the important case. So positive torques. Okay, so the next thing that we wanted to do is kind of avoid this problem of having this circumbinary disk and the mini disk. So we zoomed in here, and this is our computational domain, into a single mini disk, and we solved the equations of general relativistic hydrodynamics in order to have the event horizon on the grid. So we can actually solve for the accretion not as a sync prescription, but actually using a real black hole. And this is a part of the thesis of my student Jeff Ryan, who's now at Maryland. And so what's really interesting is this way. There's a whole study that's really interesting, but this is kind of the main result, is that you don't see it here. This is the zoom in, but this is the Roche surface. The other black hole is here. It's tidally distorting the accretion disk. It's squeezing the disk. And and this thing is in the co-rotating frame, so it's orbiting around. So when you include both of those effects in GR, what you get is a spiral shock wave, which is really interesting because basically what's happening is gas is trying to orbit this black hole. It hits the shock, falls in, hits the shock, falls in, hits the shock, falls in. And it's actually accreting independent of any MRI. So you don't need ionization, you don't need magnetic field, you don't need turbulence. That stuff may also be there, but we in fact find that this is a very efficient way to accrete. That's purely hydrodynamic, it's Reynolds stress. So we can get accretion. In fact, if you think about it, in almost a lot of cases where we actually observe accretion, it is in a system where there potentially could be this type of non-axisymmetric feature. But certainly in this case of binaries that are accreting, they accrete very efficiently without any MRI. So it's kind of an interesting case. Okay, so we found some interesting things in GR for these disks. We can find the shock, and here it's spiraling all the way through the event horizon. This GR hydro goes through the event horizon. And so we follow the fluid all the way through, and we find that these shocks deliver mass to the black hole. And what we can do is measure the pitch angle of this shock, which tells you how efficiently the gas loses angular momentum as it's shocked. And what we found is really interesting, this angle that measures the pitch angle of this spiral wave is predicted in non-relativistic hydro and other situations, and it's in Vineyard Tremaine and other places, but it's proportional to 1 over the Mach number. What we find is even in GR this holds. So we found this kind of new relationship for different things, but here's the Mach number and here's the tangent of that pitch angle of the shock, and we found that so we found this new relation that holds in GR. So these disks real disks are probably even higher Mach number, and so they're more tightly wound, but they probably still can accrete through this process. This is an interesting thing to look at some more. Okay, so more recently, and this is why I'm excited about this, is this is a different code called MARA, written by my student Jonathan Drake, and now we're looking at different mass ratios, because in general we expect the black holes in each galaxy to have different mass. So here's a mass ratio of 4 to 1. So this black hole is 4 times smaller than that black hole, and we're finding kind of some interesting similar things. In this case, the secondary orbits closer to the gas, So it actually accretes more gas per its own mass. So it actually is growing faster than the central black hole. So it's driving this binary towards equal mass, which is kind of interesting. So even if you start with wildly different masses, gas accretion tends to grow the smaller hole faster than the big hole. So that's important. And then we find some similarities. You see this pile up again into a lump. The lump is a little bit broader at lower mass ratio. But again, you can see this spiral shock wave, which is causing accretion. So we can turn off a viscosity in this cavity, and each mini disk actually accretes. So it accretes as if it had an effective alpha of about 0.1. So this is interesting. So this is the 4-to-1 case at 0 eccentricity. Here is a case that is maybe a little bit more like a planet. It's a mass ratio of 0.02. There's a transition at about 0.05 between cavity around both black holes. And at low mass ratio, it's more like a gap around the secondary. And you can see the secondary is accreting, and it's also kind of driving these spiral waves in the primary, causing the primary to accrete. And we find, interestingly, a negative gas torque on the secondary, but a positive net torque. So if this is like a type 2 like migration, it would actually be outwards in this case. Okay, so the other interesting thing to consider is eccentric binary. So this is really fun. This is what I'm doing right now. But if the black holes come into the center of the galaxy, they're expected to have eccentricity. So what you can see is the disks form, and then they disturb each other, and you have all this shocked gas that's traveling back out to the cavity. And then it kind of accretes again, and the disk is destroyed. So you have these intermittent flares. And people talk about tidal disruption events as being a star being ripped apart by a black hole. But this could happen on timescales of hundreds of years or something. So if we saw it happening once, I'm kind of interested whether this can produce flaring of black holes that's not due to disruption of a star. So this is an interesting thing to look at. We again find positive total torques on these unequal mass eccentric binaries, which is interesting. Okay, this is a slightly different mass ratio, but just showing that these types of characteristics are common for eccentric binaries, that you have these things, and these streams, again, are shocked and will light up the disk, and also it'll lights up the circumbinary disk. So all of these things can potentially produce bright time variable electromagnetic counterparts to gravitational waves. Sorry?
Will these ever merge?
These ones, the torque from gas is positive. So they're actually separating. But if there was something else, like interaction with stars that can be coming through, or a third black hole or something, that could drive them to merge. Yeah?
So these black holes are also accreting mass, which means that, if the strain goes like the chirp mass to the 5/3, which means that these guys, the gravitational wave signal would be getting stronger. There would be an m dot that we'd have to take into account. So this would leave a distinct gravitational wave signature if this were really happening, both in terms of this accordion kind of back and forth with the torque, and then also this increase in the mass. You would see the strain also increasing. So
yeah.
Have you looked at modeling this?
No, this is what we should talk about. This is really interesting. It means that the history of the binaries has some interesting dynamics that we should definitely look at.
Yeah.
And if this gas mass is comparable to the mass of the binary as may occur in some systems, then it's really going to affect the binary orbits. It's really going to affect the gravitational waves, and all of that is computable in this simple limit, right? Of course.
This simple limit.
Even this simple thing is already complex. Of course, you want to go to even more complicated things, but I think we really need to understand the simplest case first.
Yeah.
So even this just 2D viscous hydro already does crazy things. So so it's a lot of fun.
So, how self-similar is this going from like stellar mass binaries to mass?
Okay, so it's totally scaled out. So this could apply to stellar mass binaries in an AGN disk, as people are really interested in.
Yeah.
The only difference is that the circumbinary disk on large scales would have a little bit of shear in it, but I don't think it's that different. I think in this region it'd be similar. So these could be stellar mass black holes in the disk quasar. So this could be a LIGO source. Okay. So now for a different thing. Any questions about this before we move on?
Just one more thing.
Yes. Okay.
This would also, like, if this were happening with supermassive black holes, right? This kind of back and forth in the gravitational wave signature would increase the amplitude of the background, because you wouldn't just be having your black holes merging. They would come back out and they would do it again.
You could get stuck at a certain frequency band, which
and then you would build up a signal there.
Yep.
We can look for that.
Yep.
This is very cool.
Yeah. Okay. So I did promise to talk a little bit. Oh, so there's another one I forgot about. Okay. Sorry, this one's really fun. This is eccentric low. But look, it's kind of gravitationally focusing the gas from the disk behind it. And it's doing a really cool thing. So this is literally brand new. I've been running this like today. It's on my computer right now. So it's really cool. But again, it disturbs the primary disk, causes it to accrete. The M dots are really cool for these things. We're also calculating the spin from the spin angular momentum of the gas that's been accreted. And this is the case that would form a gap around the secondary if it were a circular binary. So in this case, that gap kind of gets filled in with gas a little bit, but there is still kind of a gap a little bit. So this kind of dynamics is really interesting and fun to do, and so we'll be doing more of this. Okay, I think that's the last one. Okay, good. All right, so topic 2. And I think this is also, it's related, very much logically related, but we're calculating light curves from neutron star mergers. And this is the thesis topic of my student Yang Wu and Zhao Yiji, who just left recently. Jonathan Drake has is working on this as well. And so this is a really cool topic. Briefly, everyone's familiar with the merging neutron star. And the thing is, O3, the third observing run, is happening now. So we expect more of these, but I'll just talk about this source that already happened. So we had 2 neutron stars that merged. It was localized. It was observed and found to be a very interesting source. It was observed in here's the spectrogram of the gravitational wave source, but then it was interestingly observed by Chandra, but not immediately. So for about over a week, there was nothing. And Chandra stared at it. So there was nothing. It was completely dark. But then at day 9, about a week later, it came up as a source. So really interesting. It was something that hadn't been seen before. And it was detected, in the VLA. There's a kilonova from the ejecta. It's a really fascinating source, really fascinating. Okay, so let's try to understand this. So it's a huge topic. I'm going to try to focus on this thing here, which is there's the merger, there's the ejecta that causes the kilonova. There's really interesting physics there. And then there's also a relativistic jet, which we think was not pointed at us. So it was pointed away from us. Otherwise, as it shocked the ISM, we would have seen a signal right away in the X-ray, which we didn't see. So what we're doing here is we're studying relativistic outflows formed by the binary neutron star merger that interact with the interstellar medium and produce bright synchrotron radiation. Okay, so this is what we did very early on as soon as we found out about it. And what we found is that the light curves could be fit by 2 different, here's the radio and here's the X-ray. There were people who had worked on it already who knew about these early data points. But in order to get it not to be bright at the beginning, so a normal GRB afterglow would be very bright in the beginning. But if you're off axis by about 20 degrees, then it rises slower. So you see some lower energy shock coming towards you. And as that decelerates, you start to be inside the cone. And the thing gets brighter, and then it fades. So these were our predictions for what would happen from simulations. And these were simulations run by my student, Zhao Yiji. And so there were 2 kind of classes, and what we call a narrow jet and a wide jet. We don't really know what happens when neutron stars merge. We don't know how the jet forms. But so we took 2 models. But one was narrow and one was wide. But the really cool thing is, since we have a moving mesh code, is we started on the scale of the neutron star ejecta cloud. And we put in a jet where the black hole we think formed. And we allowed that to propagate through the cloud, break out of the surface of the cloud, which is already expanding at a 0.1 or 0.2 C, and then expand homologously, and then eventually sweep up the ISM and form a shock. So all the way from the scale of about 10 to the 7 centimeters to 10 to the 18. So 11 orders of magnitude, self-consistently in one simulation, which is really the power of Lagrangian multi-D hydro. Okay, and so I love this picture. So that's the shock wave. That's what we're looking at. This is the kilonova or whatever. This is the ejecta from the thing itself. This is just a bomb that failed to explode. Let's see. Wait, hang on. But what we see is this shock wave. You see this thing right here? So basically, kinetic energy from the explosion is launched a blast wave into the surrounding medium, and that thing accelerates electrons, probably generates a magnetic field, and produces synchrotron radiation. That's the idea. So we're not looking at the ejecta itself, but the blast wave launched into the ISM by the ejecta. And so here's the dynamic range. So it's really the afterglow. This is the scales of neutron stars, all the way to parsec scales, where the afterglow the shock wave becomes transrelativistic, and eventually becomes Newtonian, and eventually becomes the set-off solution at large radius, because that's an attractor for any type of explosion. Okay, and we follow all of that dynamics. So the idea here, this is an older simulation, but it just nicely shows that a relativistic jet can burrow out of a cloud or a star, because what it does is it pushes the stuff in front of it into a cocoon, and you have gamma 100 material that's going to break out of this cloud. So you might think if you have a cloud, there's no way to get a relativistic explosion, because all the mass will get swept up, but it'll just decelerate. That doesn't happen. If you have an engine that keeps on pushing, it generates a cocoon around the core of the jet, and the jet can break out as long as the engine keeps on pushing long enough for the ejecta to escape. So that's what we think happens.
Is the background at rest?
Sorry, that background was at rest because that was a star. That was actually for a Clopstar. It was an older simulation. But all the simulations we're doing, the neutron star cloud is expanding at 0.2 C. And that's actually really interesting. Paul Duffel has done some really nice work on this, where that affects the jet. So, because it's a different dynamics, right? You're shocking something that's already moving fast. So that's really cool. But we include that effect. The other thing I meant to show you here is some really interesting scalings. So hydrodynamics, you can rescale. And so what we find is that the same simulation can be used. So this is a simulation we didn't need to do, because we could have just rescaled space and time and the explosion energy, and we would have gotten the exact same thing. So basically, if we do one simulation of a jet, we can scale that to any energy of the jet and any density of that interstellar medium. So that's what we did. We did a suite of simulations that covers all possible jets. And then from that, we use a synchrotron radiation model. This is as a function of frequency. It gives you the flux. And it's a parametrized model for synchrotron emission that's well known and works really well for GRB afterglows and other sources as well. And from the simulations, we can cut, here's the jet, just schematically, but we can cut slices so that we can calculate a light curve for any viewer with respect to the jet axis. So we can even do like an orphan afterglow, or we can do someone who saw the GRB, or someone who's just off axis. So we calculate light curves for viewers with any orientation with respect to the jet axis. Then we found this really amazing thing, that the light curves themselves scale. So once we've done our simulations and calculated this light curve, this is the counter jet. That's the jet was moving away from you and it just decelerated and you start to see it. But anyway, we can rescale things in order to produce light curves in microseconds. So we can generate millions of light curves to fit the data. And this is this package we call scale fit or box fit. And it's used to, if you've got some data points, you can generate theoretical light curves very quickly. And because you can do it very quickly, you can do it in a Markov chain Monte Carlo approach. So you get PDFs of all the model parameters. And you can constrain things like the opening angle of the jet and the viewing angle of the observer, and so on. Okay, so these are the model parameters. It's just a list: the redshift, luminosity distance, the microphysical parameters, the opening angle of the jet, and the observer angle. So these are model parameters. And so early on, Jeff Ryan, a few years ago, did this for the swift gamma ray bursts. So these are gamma ray bursts that were observed in the gamma rays. So presumably we were on axis of the jet. But what he found is that we weren't directly on axis. We were actually off to the edge. And if you think about it, that's what you just should expect, right? Because there's more solid angle on near the edge of the jet. And so we found really good evidence here, which is kind of beautiful, that the typical burst is observed by a viewer 2/3 away from the, when you correct these light curves for the viewing angle then, what he found is that neutron star mergers could survive. They had been ruled out in certain bursts if you misinterpreted the light curves and overcorrected what's called EISO for the viewing angle. you overcorrected and found that there were energies that were larger than a neutron star could deliver. We found that that's actually not true because there was an overcorrection when you do it properly, assuming you were viewing it from 2/3 of the way towards the edge of the jet. The energy came down just beautifully below the neutron star limit, which is interesting.
And how does this jive with what the population statistics are now for the binary neutron star mergers? Because they were hugely overestimated before, right? So does this make them even larger, and then is that consistent with what we're observing?
Okay, so I'm going to get to that. So for those, we're not observing them directly. The gamma ray burst is very faint. We don't really know exactly what's going on.
Okay.
So the afterglow is off axis, and I'll get to that in a second. But here, just let me show, here are the data that's at 240 days. This was a few months ago. And in all, so this is radio, optical, so Chandra, VLA, HST data. And these were our models, these blue lines. So we had two different models. And they kind of nicely, so we made this model at this time, and they kind of nicely fit this turnover. Some other models had predicted a much slower turnover. But this is an evidence for a ultra-relativistic jet beamed away from you. So what's really nice there is that these limits from Chandra at early times are fit, because if the jet isn't pointing directly at you, you don't see anything at first. You're just seeing kind of the edge of the jet, and then as that decelerates and opens up its angle, then it starts to get brighter at a week later, as was observed. So from that, we can measure the angle that the observer was, us, with respect to the jet axis, and it's about 27 degrees. And that's consistent with what LIGO found, but this is totally independent. This is just from the afterglow, yes?
So I would ask you about this center, because Nakar and Piran in one of their papers, they make a point that the fact that you have such slow rise in the, that you have early rise in the radial afterglow is an evidence for some spherical component of this ejector. You disagree with this assessment?
I think so. I'm not exactly sure which claim that is, because there isn't an early rise. Yeah. Okay, and then there's TESS again, but I won't show that again. But the idea is that's just because here all we're doing the same idea, but instead of having a disk that moves azimuthally, we have the same moving mesh code, but now it expands radially. So again, we want to solve for this ultra-relativistic, ultra-thin shell of material as it sweeps through space and sweeps up the ISM. So it's really great to have a Lagrangian code that can move with this explosion. And this code is called JET, also written by Paul Duffel. And so before the neutron star merger was detected by LIGO, we had already looked at neutron star ejecta clouds and already looked at how jets propagate through them. And we find it's really hard to see in this picture, but this ultra-thin shell of material, you can already see that there's a kind of a shock wave in multi-directions. And the idea here was that the shape of the ejecta cloud can affect how well a jet is focused hydrodynamically as it propagates through the ejecta cloud. But from this, what we didn't do is calculate the...
Andrew, quick question.
Yeah.
So for jet, does it include like almost like cosmological moving radial direction in order to capture the entire dynamic range?
It's even trickier. It's so it can shear. So along each radial face can move at the local fluid velocity.
Okay.
So the mesh can shear.
Okay. And then so what do you do about the boundary conditions
On the what?
On the edge.
There are fluxes. We calculate the fluxes. I can explain this.
Not that.
Yeah.
At the end of the radio phase.
Oh, okay, so that actually moves. It's really important, and I'd be happy to describe this to you.
Okay.
But the domain, both the inner and outer boundary, move with the explosion. It's actually really clever. I can tell you more about it later if you're interested. Here's the mesh. That didn't render very well, but the point is there's these are square zones or whatever pieces of a spherical mesh, but they're all concentrated where that blast wave is, this ultra thin thing. And then it kind of moves, and you can see it expands, and it does some cool things. Okay, so anyway, I love this stuff, but so here's what matters. Here's the jet.
Friends.
Yes, okay, good. Yeah, exactly. This is the right place. But you can see this whole domain is expanding. So we're Lagrangian. We're seeing a picture that's expanding by orders of magnitude. And what you can see is the energy tends to form this very thin pancake. It's got some width, but then as it expands, it becomes thinner and thinner. And that all the zones are in this really thin shell. It's hard to see, but it's kind of beautiful. You can zoom in, zoom in, zoom in, zoom in. You'd see all the zones are in that thin shell that's traveling with a Lorentz factor 100 through the ISM. There's some really interesting instabilities and so on. But look, it's traveling now 3 times 10 to the 10, 10 to the 15 centimeters, and it started at 10 to the 6. So 11 orders of magnitude already, and it's going to keep on going. And now this blast wave is becoming trans-relativistic. And eventually you can see the log Lorentz factor is, well, it's still 100, but it's going to get smaller and smaller. Near the edge, it's only a few. And this is going to decelerate as it becomes non-relativistic. But we're saving all of this data, and we can calculate, okay, and so there's some cool instabilities and so on. We can calculate for an observer at any angle what the light curve looks like at any frequency using that synchrotron radiation model, and that's what we do. Okay, and so there's some really interesting dynamics. As the jet travels through the neutron star cloud, it develops a structure. That's called a structured jet. So the edge of the jet has lower energy density than the core of the jet, and that helps explain the shape of the light curve very nicely. And so that's a really cool thing, and it has implications for rates and so on. We eventually find, we do a lot of analysis of the explosion, and we find eventually it achieves the Blanford-McKee solution at late times, as you'd expect when you have a relativistic blast wave that's decoupled from the ejecta. So it all kind of makes some sort of sense. And then some really cool thing is we calculated the photosphere. We find that at early times, so just a few minutes or even seconds after the explosion, there's relativistic material that's escaped the photosphere. And so if we had known about the gravitational wave event and gotten there early enough, we predict we should have seen what we called a merger flash. So the light curve that we predict theoretically, this is the part that matches the data after a week or so until years. But here was what we missed. So we didn't look in the first minutes to hours. So this is a prediction for the upcoming observing runs of LIGO and Virgo, that there could be a rapidly fading flash, and then there'll be nothing for about a week, and then the blast wave that's going into the ISM will become brighter, and we'll see that.
So is that merger flash same as a breakout shock?
I think so. There's a lot of trouble with terminology in this field, but it's just, yeah, it may be. But no, it's actually a little bit different because it's escaped. Yeah. Different people have different names for these things. But anyway, so this would be earlier. So this is the light curve of the data, and you can see it's all at several days up to a week. So we're talking about something that happens to the left of this plot. And so there's some interesting analysis of that data in Kate Alexander's paper that showed there was a very steep decline in the light curve. And that favored, rather than the wide jet that I showed earlier, also called a cocoon model, this favored an ultra-relativistic jet that had that was a short GRB for someone in the universe, but not us, and that we're seeing the light curve of the afterglow off axis. Okay, so the next thing we want to do is okay, so you can take a cloud and you can punch a different type of jet in it, but how do you really know that your solution is unique? So what we did here is we used the model called the boosted fireball, which is basically a model for GRBs is just a hot explosion, which has some energy per baryon that explodes and becomes relativistic. All we do here is we take, instead of just adding energy, we also add a momentum. So it's basically like we take a fireball and we throw it. And that's with a Lorentz factor gamma. And what that expands in its center of momentum frame as a fireball, but in the lab frame, it expands into a jet. And so it's a 2-parameter model for relativistic jets. But what's cool about that is that varying these just 2 parameters, we get a whole family of explosions that smoothly interpolates between a fireball and an ultra-relativistic beam jet. And then we can use the data to determine which of those models is a better model. So that's what we did. Okay, and so we can do this MCMC, and this is a paper that I recently published, Yang Wu. And so we have all these kind of model parameters, but the important ones here are, first of all, theta observed, which is about 27 degrees. And then gamma boost tells you the opening angle of the jet. it was about 0.1. So here's a better picture of that. The result is Lorentz factor 175. The opening angle of the jet was 5 degrees, so it was a narrow ultra-relativistic jet. We viewed it at an angle of about 27 degrees, but we also have limits on that, +9 or -3, that come from these distribution functions. And so here's a CCA relevant plot. These data, where I was sitting in this room at a meeting on neutron star mergers a few months ago, and there were some observers, Raffaele Margutti, had data, and we plotted it onto our light curves. So it really nicely fit. So yeah, literally, these are the new data. And so we had gotten this kind of this break, and it's very hard to have that steep of break from a so-called cocoon model or a quasi-spherical model. So this gives us some confidence that this is doing the right thing. And this was found from the data using this Markov chain Monte Carlo technique with millions of light curves that were all varied. Energy, density, opening angle, viewing angle, all of that was varied, and found this, and the 90% best light curves are these shaded regions. And the data, the new data fit quite nicely. Okay, the other thing we can do, and I don't want to go over, as I'm about to.
I know
but,
you had a lot of questions during the
yeah.
presentation, probably stop.
Okay, I'm going to stop soon. This is the last thing. The merging neutron star was only 40 megaparsecs away. It's almost a parsec in size, right? We can resolve that. That's resolvable. So we actually made maps from the simulation of what you'd see on the sky. So these are contours. This is a paper led by Jonathan Zrake. Depending on viewing angle, you can make a sky map of the synchrotron emission. And this is what we did. So if over time, it moves. So at 100 days, it's there, 200 days, 400 days, because it's moving relativistically. 800 days. Now it's becoming a little too faint to detect with VLBI. But what we did is we did this for the 2 different types of explosions, successful jet and choke jet. We found since both of them are relativistic, they kind of have similar properties. But what you can look for as a function of viewing angles, you can independently, again, constrain the viewing angle, so you can get a better measure of theta observed. That means you can correct the standard Siren gravitational wave signal for the viewing angle, because there's a degeneracy. You get the distance more accurately, and you measure H naught. So that's a really powerful thing. Okay, so, and then we found some really cool things, which I can tell you more about if you want later, how the centroid of the image should change as a function of time, and that can distinguish between different types of dynamics. And then, after that, there was indeed a paper with VLBI, and they did indeed find the motion of the centroid. So, and it's consistent with what we had calculated. Okay, so conclusions, maybe I'll just leave them up there, but the main point is that black holes can accrete until merger. There's a counterpart to gravitational wave sources. Mini disks can accrete by spiral shocks. The torques can be positive. Binary neutron star mergers make super luminous jets, and some other stuff, but I'll stop here. All right.
All right, we have time for a few more questions, please.
So it seems like the mean density was somewhat of an important parameter in this like jet outburst. And I wonder if you've thought about including like clumpy medium rather than just a uniform density.
Yes, I've worked on this before. We did relativistic explosions in clumpy medium to calculate turbulence, and Lorenzo as well. So yeah, we haven't done that in this case, but it's a very interesting way to get turbulence, which may amplify magnetic fields. You've moved on to more sophisticated explanations for...
Or simpler.
Or simpler. Okay, but yeah, no, the clumpiness is a really interesting thing. Maybe not so much for merging neutron stars, but certainly for long gamma ray bursts, which we think are in star-forming regions, where the ISM is likely to be clumpy, and there's evidence for that, the winds of massive stars. In these systems, they're probably in an ISM, which is roughly constant density. But one interesting thing we did find about the density is the density doesn't have to be ultra low, as was originally thought. The densities kind of more comparable to galactic density are allowable. And that should be good for future emerging neutron stars, because they may be in denser environments where their afterglows will be brighter.
You said that you favored that narrow jet solution, and we're pretty far off. So, and you said it was a short gamma burst for someone else, but we did see the gamma rays from it. So,
Yeah.
where did those come from?
Those are weird, and I'm remaining agnostic. I don't know. It could be, you've got an ultra-relativistic jet. The simple model is that they're all beamed relativistically away from you. But in reality, there's probably some structure even to the relativistic jet. So, but I don't know. Other people probably have more to say about it than I do. I'm studiously focusing on the afterglow itself because I think I can understand that. I'm not so sure about this ultra-faint GRB, but certainly there's lots of people who work on that.
Further questions? Yeah.
So when you show this merger flash thing, that I noticed there is some big difference in the magenta point.
In the what, sorry?
In the Hubble optical R-band one.
Those ones?
Yeah. So,
Oh, this is Kilinova emission.
that's different.
That's a different component, yeah. These are the synchrotron.
Like a similar shape, so.
Oh, yeah, interesting. I think that's probably coincidence. But interesting, yeah.
Thank you.
So maybe there might be some trouble distinguishing. But this is early, this is really early. This is in the first, this is almost a prompt counterpart. It happens in seconds to minutes. And this happens more on a time scale of the day, hours to days. So it's a different, yeah.
Any last questions? Okay, if not, let's think in.